Okay, thank you to be here for the lecture of today. We will reconsider very shortly, with a few words, I would like to say, the introductional part of last time. Do you remember last time I introduced model predictive control, and then we will go ahead. I would like to say, as I told you before, I think to conclude today, but we will see. In any case, we can reopen some questions also next week in case you have some issues. This is an interesting topic in the context, as I told you last time. Why not? Yeah, no. The context of optimization control. Do you remember a few words? Model predictive control is the combination of what? Of a model and an optimization technique to obtain the input in order to reach some goals. Very quickly, colloquially explained. The combination of these two concepts, I would like to say. With the model, we realize the prediction. With the prediction, we will see again today, we can calculate in accordance with a constant function to be optimized, inputs or one input to be applied at each step. Again, as I told you, we are speaking about a discrete structure. I told you what a discrete structure is. Discrete structure means, now we will see again, that I need and discretized model in the sense. Yeah, this list of elements allows to see that we can see that is a powerful method. It's one of the most powerful methods. What we can do in this course is in this lecture is let me say, to show you in a very quick method to solve the model predictive control. Basically, is the method is possible to apply this method we will see today just in case of convex optimization problems. This means, you remember, basically in convex optimization problem is in a problem which you have in a convex cost function to be optimized. We will see today the concept of the convex functions again. With constraint, let me say, constraint to a linear system. Yeah. If the problem is not convex, we will see a little bit together, just roughly speaking. Of course, we need to solve the problem in a different way. We need an optimizer. You remember the concept of optimizer? We have seen one optimizer, the PSO. We have seen the PSO. Of course, in your project, if you decide to go ahead with the model predictive control, and we include different constraint, inequality constraint, we need, even though the problem is convex, because I have to say this analysis is possible if the problem is convex, but without inequalities in the context of the problem. In this case, we need a solver. Of course, we have a solver. We have seen a solver, at least one. This PSO is a solver which allows to calculate minimum, maximum, zeros, and so on. This means if you want, we can nevertheless attack the problem, a more complex problem in an MPC using PSO. This can be done through the project. Why that? Because I don't have time to apply. It is more programming. Now we have seen a PSO a little bit together. This means, considering the knowledge which we will see today and probably a little bit next week, but I think today is enough. We can consider also more complex, different problems in this sense. Okay, we can see in any case at this point here, we can see this, as I told you now, the method integrates dynamical modeling optimization, can be used can be applied for multivariable. And very important, disturbance reaction. We will see today a little bit about that. I don't know if I will simulate, it could be. But in any case, it is possible to reject really disturbances in, let me say, indirectly, but also directly. Probably 2 words about this. Is a mix, this method, between feedback control and feed-forward control. We will see a little bit more in detail also today. Discrete, I already told you that we need a discretization in order to predict. About this, I already told you we can include also constraints, upper and lower bound on some variables. But in this case, if you include constraints or explicit constraint, and to say the input should be not larger than, I don't know, 10 volts. In this case, of course, this method is not what I am presenting now. Cannot be applied. Cannot be applied. We need in any case optimizer in the sense of solvers. PSO is one of them. I would like to comment later this year. Basically, at this point, let me show you this picture again in order to recap that we have a trajectory to be tracked. These blue points. Again, why points? Because we are speaking about discrete signal. Why these blue Y points are the trajectory to be tracked in the future. Why that? Because the present sample or the step is k. But I can predict if I know. Of course, if I don't know, I cannot apply model predictive control. It doesn't matter how long is you remember the prediction horizon, at least one step. It is one step can be used in order to realize the model predictive control. But if I don't know anything about my future, what is the meaning if I don't know? If I don't know the goal, the blue line. Do you remember last time I told you if I know the profile of the velocity today or the velocity of a car, I can plan the velocity of a car. I can plan the position of a car. I can plan the money which I want to have in the bank. And then I can play my expenses. I can calculate, excuse me, in the context of model predictive control, my expenses and my investment in this sense. You can see here that I fix also in a set point at the end and the target, not the value. But of course, to reach this value, I can also fix different steps at each sample time. We have a control horizon. We can see here is a prediction horizon. As I told you in this lecture, we will consider control horizon equals prediction horizon. But in any case, the control horizon cannot be larger. This is intuitive to understand. The idea is to calculate this manipulated value for the future, even though I will apply just the value which I will obtain at the step k, and each time I will recalculate again, considering a residing horizon, because today I am here, I will predict, I have this goal, this blue line in the sense points, or sampled line. I will calculate my manipulated values until the end of the horizon, and then at each time I will calculate again, because I don't trust what I am predicting today for when already is tomorrow. I mean, each day this is reasonable to think that we can repredict. This is the sense of the model predictive control. Let me skip here. The idea is a little bit as in the chess. Chess. If you play chess, you can understand what I intend. At each step, you reconsider your prediction. You reconsider. We will see in detail with MATLAB. This I would like to comment a little bit more in depth. in which we have a plant to be controlled with disturbances. And you remember the disturbance play an important role. Better to don't have disturbances. But if we have, because in control, very often we have to work against disturbances, no? In order to control also the situation in the presence of disturbances. Yeah, we can see, and then we will see MATLAB a little bit better not today. I measure something. Basically, I need all states, all state variables, everything which represent the energy. Do you remember I told you this? The states reflect the energy of a system. I need all, typically. If I cannot measure, I have to observe, I have to estimate. About the estimator, I don't have time to tell you, even though we have an estimators which are optimal estimators. One of them is Kalman filter. Next semester, each winter semester, I have a course in Kalman filter in order to show you how if you don't measure everything, sometimes it's too difficult to measure everything, or it's too expensive to measure everything because we need sensors. Anyway, we need place to put the sensors in the equipment. Anyway, it's complex to measure everything, really complex and expensive. The idea is to measure in a part of the state, just a few variables, let me say, and to estimate the rest. Estimate means, in this sense, to calculate what we cannot measure, but in an optimal way. Minimize noising. Anyway, if you want to go in depth on this, in the winter semester, next semester, I have a course dedicated to Kalman filter. Using the model and discrete model, we can predict what happens in the future. The controller consists of a setup and set point. This means the goal or my trajectory, which should be tracked. I will compare my trajectory, which should be tracked, with the prediction. And then the controller basically consists of this optimization method. We will see today in a particular optimization method, which calculated the solution offline, because the problem can be solved analytically. But if it's not, the controller should really consist of an optimizer. PSO is one of them. The difference between what I want and what I have, also in the future, thanks to the prediction, we can see again here a little bit. For instance, tomorrow, the idea is to minimize this error here, because this empty dot, let me say, at the predicting. We can see here with the hat, we indicate always the predicting. And the idea is to calculate an U which minimize this difference. What I want, the blue dot, and what I have, the empty dot, until the end of the, let me say, control horizons. Because this U is involved in the controlled horizon. This U is the input. Is this here, input, or the inputs, that could be also more than one. We will consider just one input. Yeah, last time I consider this system here. For the engineer, is clear what I intend. In any case, do you remember, I need a model, a parametric model. Oh, not necessarily, but remain on the parametric model. Parametric model means differential equations. As I told you, we applied also this MPC is applied in economy. Economy a lot. In economic fields, model predictive control is applied. We applied also here in my lab. Anyway, we have two differential equations, which state the dynamics of a system. In this case, this system here, we can see we have a current and the velocity. We can express more I would like to say, this is just, you remember, from here to here is just a different language, but in any case, it's extremely important to to translate, let me say, this language here or this information here into this one, because we will see that to predict is extremely more effective, because we are working with the computers, and matrix and vectors are easy to be represented. I would like to skip this because at this moment it's not in this course it's not relevant. But now, again, the concept of the discretization. This is the model characterized by two equations, equation 1 and equation 2. The discretization which I will present in this course is the classical discretization forward Euler discretization, which is basically characterized by a prediction forward. We can see from here, which we approximate the actual current and the actual velocity, let me say angular velocity, the actual input, considering k minus 1. Why this idea here? Because the derivative is, in this sense, the future current minus the actual current, and the derivative of omega is the future omega minus the actual omega. What is the meaning if I don't know the future omega? The meaning is just in a formal way to represent in discrete form the equation 1 and the equation 2. If I plug in fact, this position here in equation 1 and equation 2, considering Ts in a simple time, believe me, after boring calculation, I will obtain the equation 1a and equation 2a. We can see that now we have a model in the sense the current tomorrow and the velocity tomorrow is a function of the current today, the omega today, the input today, and Ts. Very important, Ts, the simple time. The simple time is the time in which I will consider states in input constant. We can see from here. Last time, probably, I invested more energy. At this interval between k minus 1 and k, between, k plus 1 and k, between k plus 2 and k plus 1. We can see that everything is not exactly visible because I didn't put, but the idea is that this point does not change until this one. Here we can see very well what I intend. Basically, the value, this value here, the y hat, this level here, remain constant until k plus 2, something like that, and k plus 3. And then we will change. Basically, inside each Ts, I don't see any variation of state variables, of set point, in the sense, desired trajectories, inputs, and so on. Very important, everything depends on Ts. The dynamics depends on Ts. K could be also, in this context, be considered as the present. The present is a function of the past. I mean, this possible interpretation is not necessarily connected with the future. If k minus 1 is the past, k is the present. But typically we say that k minus 1 is the present because the idea is at the end just formally to obtain the model in the sense of a prediction. We can see that we have also here already the prediction, because the left part, ik and omega k, is the function of k minus 1. We can see here and also here. Yeah. Now, as before, I can compact this equation A1A dot 2A dot in the matrix form. We have seen last time a little bit better. I can consider to predict the velocity. I can consider to predict the velocity. This means matrix C is 0, 1. Last time I invested a little bit more time. X, as we can see here, is this state vector. If I multiply 0, 1, this column vector with this row vector, this row vector, 0, 1 is the row vector, with the column vector X, which is here, I will get omega. In the books, very often we will rewrite everything in this form, in which of k on the left part we have k plus 1, and k starting from 0 is the equivalent, is an equivalent form. Just to reflect the literature. And then I can now reconsider this slide here. We stopped last time at this slide in order to clarify a little bit the concept of the prediction. Yeah, we can see that the prediction is already in this expression here, in the frame, in the red frame. Why that? As I told you before, the velocity, the predictive velocity, which is c, which is 0, 1, multiply the state, which is current and velocity, is expressed by this equation here. But this expression here, this is a state here, state at time k plus 1. We can see depends on the state at time k and u at time k. This means already this model here in this form represents a prediction. Same consideration can be done if I use a different discretization. But of course, we have important differences between all possible discretizations which we can use. We have really big differences in many aspects. I don't have time here to analyze the differences, but you can believe me that when we have many methods, this means we have drawbacks and advantage. If you use, for instance, Beck-Euler, we have really a totally different analysis model in the sense that I don't have time to tell you about that, because the forward Euler is most used, even though not always is the more effective. It's really in a different way to represent the model, and also concerning stability, concerning relative degrees, we have big differences. This means in the project we can consider together also different discretization methods. Let me show you again, then we will go ahead, the concept of the prediction. Look, the first prediction is easy because implicitly is already directly, let me say implicitly directly, let me say so, in this equation here, because if you plug in x, this x here at time k plus 1 here, we obtain this. It's clear. Now, more clear, more evident the prediction. Tomorrow, let me say tomorrow, or the step after now, is analytically, is calculated here. Now, if I add here plus 1, I have a y hat k plus 2, and here I have x k plus 1. You input k plus 1. And of course, I reconsider this expression. Of course, when I add plus 1, this x becomes hat. Please look at don't be confused by the notation, because everything which is in the future is hat. We can see from here. If k is the present, k plus 1 is the future, therefore I put hat. I don't know if it could be that somewhere I forgot, but the meaning is clear. K plus 1 is the future, and to predict, you remember, the prediction is characterized by hat in the literature to distinguish by the present. No? But anything, we can see that tomorrow is a function of the present. Now, if I add plus 1, you have a plus 1, I have here plus 1, I have a plus 2. To obtain y hat, in any case hat, because this plus 2 is already more in the future than plus 1, I have to plug in here basically this expression. But when I had plus 1, I didn't put all information in the slide. This x becomes hat because it's the future. Plus 1 is not the present. If I plug in this expression, believe me, but it's easy to see, I will obtain this expression here. Why that? Because, yeah, I have a x hat plus 1. I have to put this, And we can see that we have this element here, C. K means is in the context of discrete, even though C does not change, but A change. No? AK is this one with respect to A, which was this one. I didn't put A, but it's the continuous matrix. Where this element come from? Yeah, basically, excuse me, where this element come from? Come from by the product between C and this element here. Excuse me. Let me see. From this comes from here. 1 second. This here, as I told you, come from here. CA square, I see here very well. Let me see, this here is easy because it's basically this one. That does not change. If I add K plus 1, remain here. This element here, let me see if I'm able to see. Yeah. Because if I have K plus 1 here, we have a C multiply A, which multiply this element here. Which when I multiply by this, we have this. But I have to multiply also by this. No? This means C multiply A multiply B, which multiply U input of K. I don't know if it's visible. Because this equation here must be considered here. No? This means C multiply A, and the element here is multiply B multiply U input in order to obtain this one. We can see that at the step 2, the predicted step 2 depends of the input at the step, let me say 0, and let me say the input at step 1. It makes sense. After tomorrow depends also what I did today, but also what I did tomorrow. Together with the state of today, which include the energy in the sense. No? And this is a little bit analytical, it's clear conceptually. I try to explain a little bit. And I can proceed until P, in which P is the predictive horizon. Of course, we can stop 1, we can stop 2. P is what I have at disposition. Of course, ideally, it should be nice if I can predict until the end of the process. But this is extremely expensive. We will see why, also with MATLAB. Let me go ahead. This information, this slide, can be summarized in this form, in which we have this equation here, which is a vectorial equation. Here, I forgot a little bit, but I didn't forget because I see the notation is consistent because I put this underline just in the matrix. Anyway, but y hat is the vector we can see here. Is the column vector of the predicted output. In our case, the predicted velocity, but could be any kind of variable. In an economic project, we considered the capital, the liability, the money which is, I have a paper if you want, the money which is in the bank, but belong to me. It's not in my wallet, because otherwise it's not a dynamical system. Because in my wallet, I don't have interest, but it's in the bank. Now, this is the row vector, which we can see here, no? In which I vectorialize the predicted. It's quite abstract because it depends on the model. But anyway, it's the predicted vector. Velocity in our case. G is the matrix, which is characterized by this element until P. This means we can see here consists of P elements. Excuse me, wait, this matrix here. We can see. F1 is the matrix in which includes everything connected with the input, in which you input, this vector here, is this one. Basically, the actual input, the input for tomorrow, which is predicted. We can see here, the input, everything which is k plus 1, or larger or equal to k plus 1, is the predicted input or the state, everything. Let me see if no, I think we can go ahead. Let me show a little bit better this matrix if you want. In particular, look, I put here in evidence 2 steps in order to understand a little bit better, no? In order to understand a little bit better. Yeah, we can see here step 1 and step 2. Why? In order to understand. And then, of course, for P step, we can extend. Why the 0 here? Because we don't have a UK plus 1, no? We can see here. In the second row, we have U input or the U k plus 1. Therefore, I copy this. Try to image F1 multiply a column which consists of these 2 elements. I think we can proceed. I am thinking if I forgot to say something, but I don't think so, no? I don't think so. Okay, now, cost function. As I told you more in detail last time, model predictive control of any kind of optimization algorithm must be characterized by a cost function to be optimized. We can see this classical cost function in the model predictive control. We consist, it seems to be difficult, but it's not. We consist of the sum of the error square, in particular weighted sum of the error square. Why this is the sum of the error square? Because if you consider now this difference between YR, which is the desired trajectory, Y hat, as I told you, is the predicted trajectory. If you remember, Y hat was a column vector. This means YR, I didn't put here, but nevertheless is a column vector. This means this way to represent is a row, the row of the error between what I want and what I want, YR, and what I have, the prediction. Q at this moment, forget it. Consider an identity matrix. Consider a weight identity matrix. This means I will weight each step in the same form, which multiply the column of the error. But if you remember, row multiply column means the sum of the product of each element of the vector. And we can see the same vector once in the row form, once in the column form. This means this is the sum of the error square. 1 divided 2 is just formally there. You can omit it if you want. Plus, we have another vector, another sum of squares, but which element are squared here? The input. Because this way to proceed is, in a way, in order that we want to minimize the error, and because this plus here. In the meantime, we want to minimize the energy which I need to achieve this error. Because sometimes, very often, I would like to say, we have a limitation in input. We cannot apply any kind of input. In the bank, for instance, I cannot think that I can invest 1 million euros per day, just to put an exaggeration. This means this is in a way to include in the cost function in an implicit form barriers. This means limitation input. It is in a quite comfortable way, because if you consider this limitation using inequalities, put in here, for instance, as the input must be less than 1 million euros per day. Of course, here it's not, this way to proceed is not more directly applicable. We needed a solver. And the idea is to avoid the solver, because the solvers, or the implementation of the solver, or to run the program with the solver, could generate delay in time. This means for some systems could be okay, but for instance, in case of electrical system which we have to electrical in the sense anyway, fast system. Fast means system which needs speed. We need to answer in everything, observer, controller, and also optimization method in microsecond in a sense. This means this is a good idea to include the barrier, to include this limitation implicitly, let me say, because the other word is explicitly with inequality in the cost function. In order to consider this possible limitation in input, the idea is to find a compromise. Optimization means always a compromise between what I want to obtain and what I am able to invest in this task, the input. Q and R is symmetric matrix. I forgot in positive. Positive defined. About that, I don't want to insist, because we have to consider a little bit more in depth the theoretical aspect of matrices. But here I forgot to say it must be positive, but it's intuitive. It's intuitive. It's intuitive because the function, the cost function, must be convex. We can see as in a quadratic form. A quadratic form. In order to be more concrete, in particular on Q and R, I put here an example with two samples, which we can see now explicitly that we have the error between what I want to attain, what is predicted. I consider two steps. Look here. We have a Q1 and Q2, typically in the diagonal form. I don't want to tell you about these anti-diagonal elements. Now, why two elements? Because we can wait what is more important, tomorrow or after tomorrow. Typically, Q1 is larger than Q2, but not necessarily, because we consider more important to achieve the goal tomorrow instead of after tomorrow. But please pay attention, this is extremely difficult, this aspect here, in particular, if you consider also this is the same concept. We have the input to be calculated for tomorrow, that today, in order to obtain the goal tomorrow, and the input tomorrow, even though at the end we will apply just U1. We can see probably from here the actual input. We'll never apply the future inputs, because after the step 0, let me say 0, we recalculate, we applied UK and at time 0, this is K plus 0. And then we will recalculate everything. Or we will see with MATLAB a little bit. Now, R1 and R2 are again the weight. I have to consider this I'm more, let me say, if for me it's more important to invest everything for tomorrow or everything for after tomorrow. This means, in this sense, if tomorrow is more, I have more availability, let me say, R1 should be less than R2. I don't know if you, again, Probably we can see from here a little bit better this concept here. As I told you, is in a balance between, in general, what I want to attain and what am I available to spend to attain this. This means for a small value of R, I am basically concentrated on obtaining the results independently of the input. This means I have a lot of energy at disposition or no constraints. The system accepts a very large input. And the same concept here between R1 and R2. Here I clarified a little bit the relation between Q and R, or this means between the error and the U. Vice versa, no? In the same way, if I consider larger Q, no? Larger Q means I would like to minimize the error, almost neglecting what I have to spend to achieve this. The same can be considered between Q1 and Q2 and R1 and R2. It depends what for me is more important. I mean, if it's more important to minimize the error E1 with respect to the error E2, in this case, Q1 must be larger than Q2. I mean, think about Q2 equals 0. This means that I'm not interested to minimize in this sense. U2, clear. Because it does not appear in basically in the cost function. Again, if I is not interested to minimize U2, I put Q2 equals 0. And then I will concentrate everything on A1. The same consideration can be done here. In this sense, yeah, I will consider R1 0 and R2 very large. It's the contrary. I don't know if it's the contrary, no? Because of course, if I want to minimize just U1, I have to consider 0 very small with respect to R2. This means I don't care about the amplitude of A1. This means this, let me say 0 very small, and this must be larger than R1. Anyway, this consideration can be done during the project, but I try now to flesh out what I intend with this way. It's extremely important because an optimization problem is always in a compromise between what I want to attain and what I am available to spend, and also in terms of present and future. I put here two elements in order to understand a little bit better. Now, applying this vectorial derivative, if you remember in high school, the derivative is just a necessary condition to calculate the optimal, because could be a minimum, could be a maximum. But in our case, we are in the presence of a convex optimization problem because we have a convex function and a linear system. We don't have inequality. With the inequality, nevertheless, we can be in the presence of a convex function. Excuse me, a convex optimization problem. But we didn't consider this in this lecture here. But we can do it with the project, but we need to apply the solver, for example, PSO. Now, this is a necessary condition, but in case the problem is convex, we have seen also in Genasio, if the function is convex, at that time we didn't consider an optimization problem in this strictly as we consider today. It was just a function. But if the function is convex, this is also sufficient, this condition. Anyway, yes, in our case is also sufficient, and doing very boring calculation, which I don't do in this complementary course, we will obtain this solution. Believe me, this is a solution which can be directly applied. Very often is applied because it's the easiest form, but extremely effective. Extremely effective. We can see that the U input, which is a vector, is the function of the prediction parts. Do you remember the matrix F1, which is related to the inputs? Very important, Q and R. Q and R, they appear in the analytical solution of this optimization problem. Also here, Q. And the difference between what I want to obtain, this is classical in control, no? In the feedback control. What I want to attain, I called here YR. At the beginning was Y blue, do you remember? Y blue. Minus G multiply X. If you remember the matrix G, now we come back, is the predicted output until the end of my horizon, as YR. It's Y hat, basically. Is Y hat. But also, but I have to say, just the part of Y hat, which depends, now we can see, which depends on the state. No? Let me see if I forgot to say something. I don't think so. Okay, let me skip these calculations. If you want, you can go through the calculation at home, but it's not necessary in this course, in complementary classes here. It's not difficult to demonstrate, but it's extremely boring, believe me. This is again the solution. Yeah, here we have some considerations which I already did. Look at this. In case we can consider U constant through the horizon, the solution becomes a little bit easier. Instead of F1, we have an F1 tilde, which is defined in this form here. It's a simplified. Remember, F1 was a little bit more complex, but it's easy to see because if U is everything the same, we have just one input. Which one? UK. Which is equals in all steps. This means we have just, let me say, if you have just one input, in this sense, we have just one column, CB, and then this element here plus this here, because the second element is equal, the second input is equal the first one. And then we can generalize for the rest. Could help. Could this help? Yeah, sometimes, because in order to simplify the calculations, because how possible to say, very often we have a system with a slow dynamics. Sometimes the sample times could be very small. In particular, if you have, could be very small. And then the changes between UK plus one and so on is relatively small. It could be considered to simplify the calculation. As I told you, one of the problem is the calculations. In particular, if you have a very long control horizons or prediction horizon. In our case, both. I mean, we have a condition control horizon equals prediction horizon. Let me skip this. Look at this, another variation. If I consider now UK minus UK plus 1 equal delta UK, this means UK is equal delta UK plus UK minus 1, we can rewrite the problem in this form here, in which we are looking for, the delta UK, the variation. it's another form. It's another form to obtain the solution. Remember, before we calculated directly u capitalized of k. It's basically the future vector of the input. Here we are considering the difference. Basically, you can say to me, but please pay attention. We don't have many changes because uk minus 1 is known. The difference in between is delta u. In fact, the application we cannot really realize many difference, but in any case, it's a little bit easier to be tuned. The system is easy to be tuned, as if basically we are considering just the difference between uk and uk minus 1. And in some cases, we can consider it's easy to be tuned. To be tuned, what is the meaning of to be tuned? To calculate the value of Q and R. To calculate the value of Q and R. The reason is we will see now the solution depends also of uk minus 1 directly. This means it seems to be that the solution has more inertia, let me say, because depends of the past. Therefore, somehow is easy to be tuned. Easy to be tuned means also to consider Q and R, which stabilize the controller. About the stability, I didn't tell you anything. It's not included in this analysis. It's not included. Yeah, if you do again the calculation of last time, this means if we reconsider the prediction and so on. Believe me, and then we do again this boring calculation to calculate the minimum. This is basically I summarize everything in the prediction. I didn't put the calculation as before. Basically, what I didn't put. I didn't put this, but the concept is the same. No? Instead of u, I have a delta u. And believe me, a little bit boring. If you want, I put here the literature, you can find it in the literature. At the end, I have a similar expression. Similar to what? Excuse me if I go up and down. Do you remember this? I clarified this. No? This I clarified, in which I summarize the information which you have here and this form here, in which the matrix G and F1 is here. If I do the same calculation in the form of delta, very boring, but the same, basically, formally the same, I can write, excuse me, I can obtain something like that. We can see here, instead of u, I have a delta u, but we have also u input, of course, u of k minus 1, because everything now depends on the past. We can see that we have an element more somehow. Doing the same in which the matrix F11 and F2, in this case, I didn't put the boring calculation, can be seen in these two forms. And this is the solution after doing this vectorial derivative. We can see it's quite similar. Of course, we have different matrices. The unique difference, structure different, that we have to consider also the past. I already defined F1, F11. G is the same. G is the same as in the first variation. F2 is here, which looks like this is what I told you before. This here is the same, basically, because uk minus 1 does not change formally at each step. In the presence of disturbance, I'm concluding, then we will simulate in the presence of disturbance. We can see here that the system consists the disturbance, which we can consider constant in this analysis. Constant is not basically it's a big it's a conservative assumption, because constant means practically that the dynamic of disturbance is not faster than the dynamic of the system. Anyway, let me go ahead with this analysis. This D here is the constant. If I do again here the analysis of the prediction is a little bit boring, but again, is basically what I explained before. If again this is constant, I put here in the literature, the solution using always this boring calculation, the vectorial derivative of the cost function, which remain the same. The cost function remain the same. I will obtain this solution here, in which we have the solution of the delta version. Here is calculated in delta, minus F3 multiplied D of K. Basically, it's the cancellation of the disturbance. This means the disturbance cannot be known, because otherwise it's not a disturbance. I can estimate with an observer, with a Kalman filter for this. And then I can apply this. Really, I need to apply this. Really, it depends. If I want to, let me say, at least mathematically cancel totally the disturbance, I need this. But also, this variation here, what is it's sensible to the disturbance because of the feedback which we have. This means we can attenuate, we cannot cancel totally the disturbance, but we can attenuate. But also the first variation, because of this feedback, is sensible to the disturbance. This means if for us it's too expensive to implement an observer in terms of the measurement, no, because we reduce the sensor. In terms of calculations, we can apply, for instance, this or the other variation. Okay, I would like to now to at least introduce a simulation. And then I need a little bit also the lecture next week to reconsider a little bit the simulation. It could be that I will show you the variation of the disturbance too. But we can see also today now that we can see also, where is? Here. We can see also today that also in the presence of the disturbance, we can effectively work with the first variation, even though the disturbance is not explicitly known. But of course, we need a higher value of the input. It's clear. Yeah, we can see. Because it's not so sensible as we have the disturbance estimated and we implemented it in the solution. And not only, we cannot cancel the disturbance totally. But anyway, we can reduce the effect of the disturbance because in any case, we have a system which consists, a control system which consists of a feedback. Let me share. I go ahead with the simulation, then I will upload in my study for your project, of course, because if you decide to apply this, it is enough to download. We will see in the project we can apply it also with disturbance. We will see that the differences are really small. Just in the final equation. About the disturbance, I will tell you next week quickly, and then we will change topic. Let me now show you this scheme here before closing. Now I hope that I can find quickly, because to find material in my folders sometimes really is challenging. 1 second. It could be that I find, nevertheless. Found it. Okay. I think you have you seen MATLAB, I hope, no? Yeah. Look here. Exactly the motor which I presented in the lecture, but in a real motor with the real data. But we can see here, in any case, the matrices. TS, I don't know why it's so strange, because sometimes I don't remember, but you can change. Yeah? You can change. Of course, the choice of TS is not irrelevant. I told you probably last time. Could not be very small, could not be very large. Very large is intuitive because why the approximation of the signal is also very rough. You know? So let me say, roughly speaking, I cannot be also very small because now I don't have here the expression of the discretized matrix. But if TS is very small, let me coming back on the lecture to repeat what I told you last time. If TS is very small, look what happens. The representation in the microcontroller, I don't know if I share, I hope yes. The representation in the microcontroller becomes, we can see, directly here is easy to see, becomes not controllable because we have here zero, almost not controllable. Then directly from here. But also this matrix becomes diagonal. No? 1, 1, 0, 0. No? 1, 1 in the diagonal and 0, 0 in the anti-diagonal. This means the system is not coupled. I cannot control. Of course, in the representation, this means we cannot find a suitable solution in this sense, because the representation is responsible for the solution. If the system is not controllable, how we can generate and almost not controllable and a suitable U. U will be extremely large. But we will see together in the project. Okay, we can realize here in different form. I don't remember, I told you about this, a little bit about the forward Euler discretization, but you can use also directly from MATLAB. This is the exact discretization, not exactly forward. Not discretization, but you can see that in different courses, I try to compare this from MATLAB. In MATLAB here, you can select with an option also the forward Euler. Look at this, help C2DM. This means continuous to discrete mode. If you don't like this, you can activate this discretization here, and in this sense, you can proceed with the forward Euler. But you can also put in here an option to consider directly the forward Euler in this discretization here. But about the discretization, eventually we can look together some issues in the project. I don't have really time because it's a big topic. Anyway, look, I put here the matrix F1, the matrix G. I put also F2, F3. I put also F11, all possible matrices which we have seen in our lecture, because I used just one M file for every variations. Here I put Q and R, even though I think I reconsider Q and R in the specifically in each applications. Let me open Simulink. Why I put here again? Because I use just one M file for all possible variation. We have seen different variations. I will continue this a little bit, but just in the part of the lecture of last time. Few minutes, I show you the Simulink structure, because the Simulink structure is extremely easy, because I have to apply just one equation, the solution. But of course, the Simulink, nevertheless, is I need to define the desired trajectory. We can see also here that I lowered the data trajectory. It is written that I saved my velocity profile in an extra file. Simulink a little bit heavy because I needed to manage the data. I have to manage the trajectory. I have to run everything with the trajectory. I have to show you what I'm measuring. But conceptually, I have a feedback system, of course. I generate an error between what I want to attain, this desired trajectory, and what I will predict. I will show you a little bit. Let me share. I forgot to run. Let me run the data. I'm so stupid. 1 second. Let me share. I already share. Yeah, we can see in this block here, we have a vector characterized by the time you can find in this data trajectory, data trad. If you load, you can see that you have a vector of the time, and the vector vel is the desired velocity. Calculated at each step time. TS was a strange number, but you can change. If you change, I think it's not a big problem, but I think it's not a big problem. Like you can check, change. The DC motor is characterized here inside, which we have the matrix A. I don't know if you remember. Let me show you. B and C. Which I call BR, CR, D, and so on. We can see that we have also another column in the matrix B because I considered here the disturbance. Because you remember I told you the scheme is also suitable in the presence of disturbances. Let me share again here. We can see that I measure both this and this in order to predict, and these two element current and velocity go here inside. Let me show you better. On MPC, we don't have here the variation UK-1. Do you remember? UK-1 belongs to the variation delta, which can be used alone or can be used with in the presence of disturbance. Here we will see the algorithm extremely easy. Spook, excuse me, calculate UK, and this UK we can see here with this go to from, basically this is from, excuse me, go to, and go to here an input to the system. The first component of B matrix or B matrix is the input. And the second component, the disturbance. At this moment, I can cancel the disturbance. Let me go here inside. Now, here we have an max. I use in here an interpreted function. Of course, if you use an embedded function, it could be a little bit easy in the sense of simulating, but more complex in the sense of the software, because you have to consider inside some variations. But anyway, you can use both. This is what I upload. At this moment, I found quickly this. The states, current and velocity. Here I use this as an counter, because in the ramp for the time, because of course everything is updated in the time. And this I don't use. Here inside, we have a file to be open, an M file. In this interpreted structure, with this an extra file. Embedded is in accordance with the name. You don't have an extra. You don't have an extra. I mean, it is an extra, but it's inside Simulink. I don't know the concept of Simulink light. It's a shame I don't have time to really analyze. Let me show you the M file, and then next week we will come back a little bit on this, and then I will clarify also the D version in the context of delta U. You can see here that this block Simulink calls this function here. This is the name which you can find inside this embedded function, which I show you. Global means the variable which I need to be read from everywhere. Every parameter which I need. We can see that not all parameters or variables are useful. I copy directly. It's not an error. Here I recalculate Q and R because you remember I showed you that Q and R were in the M file, but because this is the general M file which you use for every kind of variations. Here we have the vector. This T0 is the time. You remember I consider the time considering this the slope and a discretized slope. I don't know if it's. Let me show you again this. That the input tree here inside is the discretized slope. Is the time. Then we have the states characterized by this column. Do you remember the states are characterized by, or the state vector is characterized by a column in which we have the first input and second input of the max. The max realized in a vector. Realized in a vector. You don't use this, the element 4. This was UK-1. I don't know if you remember. Here I try to be more precise with the counter. K index of the vector. Can be done for each TS. I round T0, the variable, divided TS plus 1. This is the round of this. And then you look here. We have the vector of the desired velocity. Of course, here I consider just 4 elements as an horizon. This means the solution will be calculated at each step of the simulation. But the horizon consists of just 4 elements. I will calculate 4u, but of course I will apply just the first one. Solution is here. Here everything is commented. The solution is here. I copied basically the solution which I tried to clarify today. Then, very important, U is a vector with 4 elements. I will apply just the first element because the second, the third, and the fourth one, I have to recalculate in the next step. And the horizon go ahead with this window with 4 elements. Let's go ahead because we can see from here practically. Because of K, it's running through the simulations. We will come back next week. Let me show you now quickly 2 simulations, and then I will conclude. If I run, I hope it is working, because sometimes at the end of the previous lecture, I changed something, and then I forgot to. Yeah, it seems to be working. Let me show you what happens. Yeah, we can see an extremely fast controller because if you realize I canceled the disturbance, but we can see that we have a different initial conditions and the controller work very quickly because probably I have a very large Q and very small R, because I don't know if you remember, I cancel the disturbances. We can see how it's working, achieve very quickly the goal. Now, if I include the disturbance, let me show you the input. Here's the input. We can see at the beginning we have a very large, no? Because we pretend very how much is, I am not able to read. Did you read here? Minus, let me see, 150, something like that. Yeah. Let me now include the disturbance. Second. I'm finishing with the disturbance. Now, next week, we'll consider the scheme delta U with the disturbance. If I include the disturbance, running, let me open. We can see it is controlled more or less as before, because now I will show you Q and R. And of course, we don't have any big differences. Show you the input, because it's the maximal probably Q which we can yeah, more or less a little bit larger. No? Before was 115 and 200. No? What is here? 200, something like that. No, 108. Yeah, more or less as before. But why that? Because we have like in the saturation the inputs. The reason is, and then concluding, yeah, look, this is in Q and this is R. Large and small, we have to simulate, but believe me, if you increase the disturbance, you can realize what I intend. Now I increase the disturbance, we can see that the controller is not exactly as before, even though the error is not as before, even though the input is the same. Nevertheless, still okay, but increasing, you can realize that the controller is not so. In my opinion, we can check next time. We have the situation that we have the maximal U or something like that. I don't know if it's the maximum. And this, of course, we have some limitation in the, let me say, in the presence of the disturbance, because the disturbance, the controller see the disturbance through the feedback. Again, using this method here, we can nevertheless control the disturbance, but we have to pay delay or larger U with respect to the system of the disturbance. Next week, we will see again this problem of the disturbance inside the disturbance itself. It could be that I will reconsider this, but we can see that. Let me simulate again a little bit with 100 probably. We can see that nevertheless can be controlled. Now we can see. a little bit better. A little bit. We can see that increasing the disturbances, we have some delay, and also here we have some. Of course, if I increase Q, I will increase. I will increase the input. I increase Q now. Let me show you. Should improve the error. Improve, I mean reduce. Yeah, we can see. We have an overshoot. We can see the differences. But of course, we reach somehow earlier than before. But of course, we pay this in terms of inputs. Let me show the inputs. Should be large, no? Yeah, we can see. I show you. This is more larger than 200. You remember last time was around 108. Yes, 200, we can see. But nevertheless, we can use. Of course, if we are able to pay in terms of calculation time an estimator for the disturbance, we can use the other variation in which the disturbance is considered. Here, the disturbance is considered indirectly in the feedback. We will see next week this variation with the disturbance inside the variation delta O, which is quite similar to this one, a little bit more robust, I would like to say, in the sense easy to find Q and R to stabilize the system. I didn't tell you much about the stability, but think about is not including the analysis. But of course, depends of Q and R. Again, if R is too small, Q is too large, it could be that we have an unstable solution. The solution, the stability is not included here. Of course, depends on the length of the prediction, but we didn't include the analysis of the stability in this context. Okay, today is concluding. Next week I will consider a little bit this disturbance D, but it's to say the solution, the structure is the same. I have to add just this matrix F3 and so on. And then we will change the topic. I think we will relax the course. I will consider the Lagrange. It could be that from some economic students, economic in the sense, could be useful so to consider this method here very easy, but important in the application for economics. Okay, thank you to be here. We will see next week at the same time. And I am here for answer your question, I hope. And otherwise, next week.